You know what's wild? Right now, there are invisible rays passing through your body. They're going through your walls, your phone, even the air you're breathing. Here's the crazy part. We use these same rays to see your bones. Have you ever wondered what X-rays actually are? They're not magic. They're pure chemistry and physics working together in the most fascinating way. Let's rewind to 1895. Wilhelm Rontgen is in his lab messing around with cathode ray tubes, basically fancy glass tubes with electricity running through. Notices something bizarre. A screen across the room starts glowing even though it's covered. There's no light touching it. Nothing visible anyway. Rontgen's confused. He puts his hand between the tube and the screen, and bam! He sees the bones in his own hand projected on that screen. He literally discovered X-rays by accident and saw his own skeleton. Talk about a plot twist. Here's what actually happened at the atomic level. When high-speed electrons slam into metal atoms, and I mean really slam into them, something incredible occurs. These electrons knock out the innermost electrons from the metal atoms. Think of it like a game of atomic billiards. When those inner electrons get kicked out, electrons from higher energy levels drop down to fill the gap, and when they drop, they release energy. Not just any energy. Electromagnetic radiation so powerful it can pass through soft tissue like it's not even there. Now, X-rays aren't alone in the universe. They're part of the electromagnetic spectrum family, sitting right between ultraviolet light and gamma rays. Same family as the light you see, the Wi-Fi signal on your phone, the heat from your microwave. Here's what makes X-rays special: wavelength. Their wavelength is incredibly tiny. We're talking about 0.01 to 10 nanometers. To put that in perspective, that's about the size of an atom. This is the key to understanding everything. The smaller the wavelength, the higher the energy. X-rays have so much energy packed into such a tiny wave. When they hit your body, most materials just can't stop. Water molecules in your skin, they pass right through. Protein in your muscles, no problem. Calcium atoms in your bone. Now we're talking. Those dense, tightly packed atoms actually absorb X-rays. That's why bones show up white on an X-ray image and everything else looks dark. It's not that X-rays magically only show bones, it's that bones are the only things dense enough to block them. So how do we actually create these X-rays on demand? Let's break down an X-ray tube, because this is where chemistry meets engineering. You've got a vacuum tube, all the air sucked out. On one side, there's a cathode, which is basically a heated filament that shoots out electrons. On the other side, there's an anode, usually made of tungsten metal. Here's the secret sauce. Why tungsten? 3 reasons. First, it has a crazy high melting point, 3,422 degrees Celsius. Second, it has a high atomic number, meaning lots of protons and electrons to work with. Third, when electrons smash into tungsten, it's incredibly efficient at producing X-rays. When you crank up the voltage, we're talking 25,000 to 150,000 volts. Those electrons accelerate like crazy. They're moving at nearly half the speed of light when they crash into the tungsten anode. 2 things happen. Some electrons create Bremsstrahlung radiation. That's German for braking radiation. They suddenly decelerate. Others knock out inner shell electrons from tungsten atoms, creating characteristic X-rays specific to tungsten. And boom, you've got your X-ray beam. The real chemistry happens when they enter your body. 3 main interactions occur. First, photoelectric absorption. This is when an X-ray photon transfers all its energy to an inner shell electron, kicking it completely out of the atom. This happens mostly in dense materials like bone and calcium. Second, Compton scattering. The X-ray photon hits an outer electron, loses some energy, and bounces off in a different direction like a billiard ball. This is why radiologists wear lead aprons, to block these scattered rays. Third, and this only happens with super high energy X-rays, pair production, where an X-ray photon near a nucleus converts into an electron and a positron, pure energy becoming matter. Einstein's E equals mc squared in action. Your bones stop X-rays through photoelectric absorption because calcium has more electrons in more tightly bound shells than the carbon, hydrogen, and oxygen in your soft tissues. All about electron density and binding energy. X-rays aren't just for broken bones. X-ray crystallography. This technique won scientists 8 Nobel Prizes. You shoot X-rays at a crystal, and the way they bounce off tells you exactly how atoms are arranged. This is how we discovered the structures of DNA and proteins, and even how drugs interact with diseases at the molecular level. Airport security, X-ray scanners. They work on the same principle. Different materials absorb X-rays differently. Organic materials like water and plastic look orange, and metals look blue. That's pure chemistry determining color. Even in space, we use X-ray telescopes to study black holes and exploding stars because hot cosmic objects naturally emit X-rays. So next time you get an X-ray, remember, you're not just taking a picture, you're witnessing high-energy electrons colliding with tungsten atoms, creating electromagnetic radiation with wavelengths smaller than a virus, which then interacts with the electron clouds of every atom in your body, getting absorbed by calcium while passing through everything else, all to create an image on a detector that reveals your skeleton. That's not medical magic, that's chemistry.